Good morning, everybody. How are you today? So glad to have all of you back. I'm really excited about today. We got some cool stuff going on about heat energy and thermal expansion. But I want to say that Mr. Seed Live is brought to us by the Dayton Metro Library and our friends at PBS Night TV. Thank you for all of your support. And we are going to get started. I don't know if you can hear the pitter-patter of our puppy dog. He's running around. He's usually sleeping on the couch right now, but he's like, oh, what are you doing today? You dropping stuff in the kitchen that I can eat? So it's one of those days.
He's worried about the caterpillars.
He is worried about the caterpillars. And did you see the caterpillars? They are getting so big. It's awesome. They're like getting jumbo. So we're going to get started today with an activity. And I just want to walk through it and we'll talk about what happens as it happens. So I have some ice water and I'm going to pour in 200 milliliters of ice water. I don't want the ice cube though. Come here, little ice cube. Alright. And then I made that blue water on purpose because we identify cold water with a blue handle. And then I have some hot water here that I brewed. And we're going to, oh, look at that surface tension. Pouring it all over the place. And I have 200 milliliters of hot water. Now, what we're going to do, hold on, I've got a napkin right here. Swipe off the red. I have these thermometers. I hope they're working. I'm going to put one into the ice water and one into the hot bath. Alright, so the ice water, oh, that one's acting up. Here we go. So my ice water is, the temperature is dropping. I don't know if that camera can get any of this, Mrs. C. I doubt it, but I'll have to just talk about what's going on. Alright, so our hot water, and we're going to talk about degrees in Celsius. It's 62 degrees Celsius.
If you come a little closer, you might be able to.
You think? It's the next one that I want to try. And then this one here, the cold water, is at approximately 5 degrees Celsius. And our hot water is approximately 62 degrees Celsius. So what I'm going to ask all of you is, I'm going to pour these 2 cups of water into this beaker. We have 200 milliliters of cold water, 200 milliliters of hot water, and we're going to mix those two together. So we should have how many milliliters of water total? 200 plus 200 is 400. But my question is, when I mix them together, right now our water is at 5 degrees Celsius, and our hot water, it dropped to 60 degrees Celsius. So we have 60 degrees Celsius and 5 degrees Celsius water. When we mix them two together, are we going to have 65 degrees Celsius water? Let's give it a try. All right, here we go. Here's the trick. I'm going to pour these in, and then I'm going to put the thermometers in. I'm not sure if we'll be able to see it, but we're going to watch what the thermometers do. All right, I'm going to pull these out really quickly. Hot water, cold water, and I'm going to put them together. So what I see is I'm seeing my hot water thermometer go down. Oh, it fogged up. My hot thermometer is going down and my cold is going up. And they're almost meeting. They're almost meeting. And I'll tell you where they're meeting here in just a second. We're at 30. We're at 31. They met at 31 degrees Celsius. 31 degrees Celsius. So roughly 30 now. So they're at 30. So that's interesting. So we had hot water that was at 60 degrees, cold water that it was at 5 degrees. And when we added our liquids together, we added that total, the volume up to get 400. But when we add the water together, the temperature wasn't additive. It didn't add on top. So it wasn't 60 degree and 5 degree and make it 65 degree water. It was actually 60 degree and 5 degree Celsius water, and the hot water got colder and the warm water got, Hot water got colder and the cold water got warmer. And the question is, why? Why? So we've also done some experiments here in the kitchen, and we can do it again because I have some water left. We've watched, oops, it's already red, but we can talk about it. The red water, if you remember, we dropped food coloring into the hot water, and those molecules are bouncing around into each other much, much faster than what was in the cold water. All right? The molecules in cold water are not moving as fast because they don't have as much heat energy. And what happens is the hot water molecules are bouncing around, ding, 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 ding. And when they come into contact with a colder molecule, they bounce into it. And they start causing it to be in motion. And what happens is the hot water loses energy as it bounces into the cold water molecules. And the cold water molecules gain energy. And eventually they start moving around at the same rate. So what we have is we have something called equilibrium. It's when those two temperatures of the different waters come together. All right, so that's pretty cool. And the reason I wanted to say that is because hot water and cold water are not, temperature is not additive, okay? Energy, we can add different amounts of energy together that have more total energy, but we can't just add the temperature of water. So that's something you could do at home with a family member, obviously because it's using hot water, something you ask for help with because we want you to be safe. But that's kind of the first step to what we're talking about today in terms of thermal energy and water. All right. So we also, are those out of the way? Mm-hmm. Okay. I'm moving things so that we can not block the camera view. So we can take this idea, and you can try this at home also. What if you have not equal amounts of water? So because we had equal amounts of water, our temperature came right almost to the middle. Right, 30 degrees was right almost in the middle between 60 and 50, all right? But what if you have 400 milliliters of hot water at 60 degrees and 200 milliliters of cold water at 5 degrees Celsius or 0 degrees Celsius? Where does the final temperature, where does the final equilibrium fall? So you can start changing the amounts of water and experimenting to see what happens there. It's kind of fun. But this idea that these water molecules are moving faster and bouncing around is something that we're going to kind of build on. And I have this, where are my goggles? So what we're going to do now is I want to show you an experiment. It's a demonstration, but we're going to talk about what's going on. Put my goggles on. Before I do this, well, yeah, let's try this first. I need you to find a piece of metal in your house. Something metal. So if you're watching this in your living room, find something metal that you can grab for me right now. All right? So I want you to grab it. And what I mean is like, you could get a spoon. You could get a spoon. I just grabbed this. It was closer. But nope, I don't want you to grab a fridge. I want you to grab something sitting in your room that is just sitting there, okay? So I'm going to grab the leg of this chair right now. And I want you to think about what it feels like. Describe it to yourself. Does it feel cool? Does it feel warm? What does it feel like? All right? So, and then I'm going to grab the other side where I haven't touched it. Man, that does feel really cool. It feels cold. All right, and then I'm going to grab something else, and I just happen to have a piece of wood here on the table, and I'm just going to touch the wood. So you should try this. Maybe touch the couch or touch the chair you're sitting on. Does it feel different? It does feel different. The metal feels cooler to the touch versus the wood feels warmer, right? Would you guys agree with that? That it might feel warmer? But what if I told you something? What if I told you that these two objects that are sitting in my house have the same exact temperature, all right? And we're going to use the water as that example. So I have a little heat gun here, a little temperature gun. This is 69 degrees. And this is 69.1 degrees. They're the same temperature. I'm going to take the temperature of the table right here. 69.2 degrees, so almost the exact same. I'm going to take the temperature of my cabinet wall back here. 69.4 degrees. So everything is about the same temperature in this room, even though some things feel different than others. So when I touch this metal, it feels really cool. When I touch the wood here, it feels rather like almost neutral. It doesn't feel cold, it doesn't feel warm, it just doesn't feel as chilly. And then I can touch the glass. It feels different. But they're all the same temperature. And my question is, why do these objects feel different? And it's because they absorb heat energy from us differently. So our bodies are approximately 98.6 degrees Fahrenheit. So if I take the temperature of this table, which is 69.5 right now, it's bouncing up and down a tenth of a degree. When I put my hand here, my body is warmer than this tabletop. So the molecules in my body are behaving differently because we're producing heat energy as humans. Heat energy is being taken from my hand to the tabletop. And the metal sucks the heat energy faster from your body. And that's why it feels colder, because you're losing heat energy faster than the tabletop or the wood. And then it brings me to this. What is this? It's a styrofoam cup. And when I hold this, it doesn't feel cool at all to the touch. It just feels like nothing. But if I take its temperature, I'm taking the styrofoam cup's temperature. And right now it's at 69.9, and that's because I was touching it and it was getting a little bit of heat energy. But styrofoam we know is a good insulator. So objects that take heat energy very quickly and rapidly, we call those good conductors. Things that don't take heat energy away as quickly, we call those insulators. A lot of big words today. Equilibrium, when things come to balance. Insulators, conductors, things that don't take heat energy, things that do take heat energy. And I want you to think about when you're outside in the summer and it's hot and you get a cup of soda or a cup of juice or water and you put ice in it. If you put it in a styrofoam cup, does it keep its temperature longer than a cup that's not insulated as well? Kind of cool, right? All right, I've got an experiment for you. We're going to do this one first. I've got these two hockey pucks. So I'm going to put them down. And what I'm going to do is I'm going to take a piece of ice. And we know that if I hold a piece of ice in my hand, it starts to do what? The camera just fell. If I put a piece of ice in my hand, the ice starts to turn from a solid ice cube to a liquid, water. And now that we're talking about this idea of heat transfer and heat energy, we know that the heat from my hand is going into the ice cube. It's causing those water molecules that are frozen to have more heat energy. They start breaking those bonds. They don't hold to each other anymore, and they turn into a liquid. All right? And my hand is really cold because it's sucking the heat energy out of it. So I'm going to take an ice cube, and I have these two. All right. I'm going to take these two ice cubes. I'm going to put them down. And we're just going to watch them for a second. Can you see both of those?
Yeah.
So this one over here, it's melting very, very rapidly. And this one over here is not melting really at all. And it makes me ask you the question, why? What is happening over here that's not happening over here? Or what's happening here that's not happening here? This ice cube is melting. It's more than halfway melted at this point. I'm just going to slide it over here. Well, I'm not even going to touch it. Look how fast that's melted. I've never seen an ice cube melt that fast. And this one isn't doing anything. And the question is why? I want you to think about it. We just introduced these two words, insulator and conductor. And not like the choo-choo train conductor, toot, toot, but like a conductor, like an object that takes heat energy and absorbs it very rapidly, or an insulator, like styrofoam, that doesn't absorb heat energy. So this ice cube is touching this plate, nothing's happening. This ice cube is touching this plate and it's melted, it's almost completely gone. So my question is why? This ice cube, these hockey puck looking things, are not made from the same material. This one here is made from a metal. This one here is made from an insulator like styrofoam. Now what's really interesting, earlier we said that our tabletop was what, 69.2 degrees roughly, right? Roughly 69 degrees. And the question is how is this melting the ice cube? So the ice cube is getting heat energy from this metal, but the metal is absorbing heat energy from the table. And what's neat is I can take this and move it away, and it feels really cold there. And if I take that temperature, it's at 59.8 degrees Celsius. Sorry, Fahrenheit. Celsius, that'd be like really bad. It's 59.6 degrees Fahrenheit. This over here, that was 59.6. This right here where it was sitting is actually at 70 degrees Fahrenheit now. So this is a really good insulator. Didn't allow heat energy to transfer through it, which means it's not giving off heat energy to the ice cube. This one allowed heat energy to travel through it very easily. It gave the heat energy to the ice cube, and it also took the heat energy from our tabletop. It sucked it out. Heat energy always travels from objects with higher temperatures because they have more heat energy to objects with lower temperatures because they have less heat energy. Because those molecules are moving faster and they're bouncing into each other, crashing into each other. They want to become equal. They want to become balanced. And that is why that melted so quickly. I love this demo. We used to do this in my classroom when I was a teacher. It's just a lot of fun to show you that different materials behave differently with different solids like ice. And it kind of, you know, when we did all of those liquid nitrogen experiments, and I said we don't want to touch the liquid nitrogen, that's because the liquid nitrogen is so cold that it's minus 320 degrees Fahrenheit, and my body's at 98 degrees Fahrenheit, so I have more heat energy. So if I get liquid nitrogen on my hand, it sucks the heat energy out very rapidly, and it can cause damage to my skin cells. So that's why it was so important. All right, we've got a couple more of these heat energy experiments. And
They want to know how cold it is in our freezer.
How cold it is in our freezer? You want to shoot it in the freezer and see what it does?
Sure.
Mrs. C's on a mission. Dun, 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 dun.
9 degrees Fahrenheit?
9 degrees Fahrenheit? Yeah, because that makes sense. What does it say when you open the door? You know how it has the little number there?
Negative. It says,
What is that in Celsius?
I don't know, 2.
So our fridge is reading 3 degrees Fahrenheit for the freezer, and this was reading like right at 9, right?
Yeah.
Okay, so there's some variation. So one of these are off. But yeah, ice cube. We know an ice cube we know an ice cube is frozen. So an ice cube is 0 degrees Celsius or 32 degrees Fahrenheit. All right. So here we go. I've got this ring. Call this a ball and ring. Put on my goggles for this. And this is brass, and it just fits through, right? So one thing I want to say is no magic tricks going on here. Just want everybody to pay attention. So what we're going to do is, this is a demonstration. This is not something that you're going to try at home because I'm going to use some open fire. And I have a torch. And what I'm going to do is I'm going to put this brass ball right into my flame. And I'm going to let it get nice and hot. And this flame is burning at a very, very high temperature. I'm not exactly sure of the temperature of this flame, but I know it's well over 1,000 degrees Fahrenheit. So we're going to let this get nice and hot. Now, a second ago, we saw that the brass ball fit through the ring, and we're going to see if this does anything. All right, so here we go. It doesn't fit. And you can see I'm pushing really hard. It's bending it. All right, it gained all that heat energy. It doesn't fit. And I'm bending. You can see I'm pushing through. But what I'm going to do is I'm going to put this in the water. Listen. You can see all the steam. I'm going to let it cool off. And if we're lucky, it fits again. So, why does that happen? This brass ball, as it gets hotter, what did it do? If it didn't fit in here, the brass ball had to do what? It had to expand. And so when things get hotter, they typically expand. Those molecules have more energy. They're bouncing around into each other. They want to expand and get bigger, and so they expand a little bit here. Let's try it again. Well, the other option would be is to what? Heat this up. I mean, it fits already. But we can make the ring larger, in theory, right? Let's try it. See what happens here. I've got an idea what's going to happen. What do you think is going to happen? Do you think the ball's going to fit through? I'm just going to put this here, let it make sure it's nice and cool. Oh wow, look how easy that fits through. I mean, there is no... It just goes straight through. So this ball and ring is a great demonstration to show you that when things get warmer and hotter, they have a tendency to expand. And I want to talk about our handle here. So this is brass. I don't know the exact specific heat capacity of brass. We could look that up, but it tells us how it gains and loses heat energy. But look at this. This metal rod is attached to this, and it's inside a wooden handle. And it makes me ask the question, why do I have a wooden handle here? Why isn't it just metal? It's because this is an insulator. It allows me to hold this safely because this rod, when this gets heat energy, the heat energy travels from this point up into the rod, into the handle. And if I'm holding metal, I'm going to feel the heat energy on my hands. It's like when you're cooking and baking at your house, and maybe you're frying something in a pan, you use a spatula, right? And the handle on the spatula is typically rubber or plastic, and that's because they're good insulators. Maybe you have a metal, the flat part, the scoop where you pick up or you're grabbing things like pancakes and things like that, but the handle is rubber so that you don't burn your hand. All right, it's thermal expansion. That's pretty cool. I haven't done this in a long time. It's since I've been a teacher in my classroom. It's been many, many, many moons. Like 13 years now. Yikes. All right, so here's another really cool experiment to try. Obviously this one you're not going to do at home because it has flame. This one is something that you can get some help with from your parents, but I'm going to recommend you don't do it. Here I'm going to take a balloon. And I'm going to... Well, I'm going to ask you, if I put flame to the balloon, what's going to happen? What's going to happen? If I put a flame to the balloon, what should happen? All right, make that prediction. Whoop, there goes the balloon. I'm going to get another balloon. Same brand, same balloon. And what I'm going to do is I'm going to put a little bit of water into it. Twist this off. That's why I twisted it like that. Okay, turn it over. And I have just a little bit of water in the bottom of that balloon. There we go. Uh-oh. Thought I heard a hole, but I don't think it was. I just had it squeezed good enough. All right, so we've got 2 balloons here. One has water in it. The other one doesn't. And what we're going to do, whoop, that blue balloon has a mind of its own. I'm not sure if how this candle's going to burn here in this fish tank. Oh, it's such a little baby. Oh, okay, it's not too bad. So what I'm going to do is I'm just going to put this down here. And when it comes into contact with the balloon, it popped a hole into it. That was kind of weak. Let's see. I couldn't find a regular candle this morning and last night. Here we go. I'm just going to put a flame to the bottom of this. Sorry. All right, so the balloon popped. The hot air from the flame touched the rubber and it caused the rubber to tear and cause it to pop. So my question is, I added a little bit of water to it. So I'm going to hold this over here just in case we make a mess. But my question is can I put this flame underneath here and what's going to happen? I know I can do it, but the question is what's going to happen? All right, start making predictions. Is it going to pop? Is it not going to pop? What's going to happen? All right, we can see the flame is touching, right? But it doesn't pop. And what's really interesting is there's all the soot from the flame. So we know it's been touching it, right? So it's not an optical illusion or anything like that. We actually had the flame on the bottom of the balloon. And my question is to you, what happened? The difference between those 2 balloons. So the only difference between the balloons is what? We have water, Wasser. So the water inside of it did something for us. It actually was absorbing the heat energy from our flame. So when the heat energy look at that. The heat energy from the flame is touching the rubber balloon, but the water is touching the rubber on the inside, and because of that, it's absorbing the heat energy fast enough to prevent the balloon from popping. And just to prove that it's a real balloon, it's the same balloon. I just wanted to prove to you that it was going to pop so that you didn't think it was anything special. The reason it didn't pop initially is because of the water inside of the balloon. All right, we've got one more experiment, kind of in the same vein, that I wanted to show you. And here I have a piece of copper pipe. Mrs. C, can you? I got it. What do we got here? Oh, Jackie was working on her German homework. First word is Hilfe, to help. All right. So what we're going to do is, I'm going to use some flame for this. We know that paper catches fire, okay? And obviously, this is not something that you're doing. This is for demonstration purposes. But this catches fire, and it will burn. All right, and what I have here is some water. I'm just going to extinguish it. Because what we're going to try is, I've got a $20 bill, and I've got a $1 bill. And my question is, do you think that I can put flame to this without them burning? Based on what we've done today. If I put this into this igniter, is this going to burn, this paper? I think we should find out. So we're going to give it a try, but I'm going to use a little science to help me. I'm going to take my $20 bill, and I'm just going to hold it here just like this. So I have my copper pipe, and I'm going to bring it right across my $20 bill, and the paper's not catching fire. And the question, but I was going to say, but the question is why? And I can feel the copper is really, really warm. Copper is a fantastic conductor of heat energy. All right? And look at this. To prove that I had it in the flame, there